All right. All right. So I've never heard of this. I don't know what the heck is going on. This section applies the theory of the preceding section to obtain an important theoretical formulas and geometric interpolation. Oh, one thing I wanted to look at actually is 3 blue, 1 brown determinant. There's a thing in this video that I wanted to look at. Where is it that he derives the formula? There we go. That's the picture that I wanted. Yeah, okay, so if you have a vector u and a vector v, a plus b times c plus d. Okay, but then you have to subtract out. Okay, I just want to draw this picture. This is pretty cool. So it's AC plus AD plus BC plus BD. But then you have to subtract out 2 times B times C. You have to subtract out AC and BD. So then the BD cancels out. One of the BCs cancels out. The AC cancels out. And you get AD minus BC. Oh, wow. That's pretty cool. All right. Cramer's rule is needed in a variety of theoretical calculations. For instance, it can be used to study how the solution of linear equations is affected by changes in the entries of B. However, the formula is inefficient for hand calculations except for 2 by 2 or 3 by 3. For any n by n matrix A, replacing column I with a vector B. Okay, fine. Cramer's rule, let A be an invertible n by n. What? What does that even mean? Solutions to AX equal to B can be written where xi is equal to the det of ai replaced with b over det a. All right, so if you can think about the complexity of computing det a is going to be this is like the most ridiculous thing. Think about how long it would take you. You have to compute maybe there's a fast algorithm to compute compute this. But that's crazy, man. That is ridiculous, man. All right, so the thing here is just making sure that you find the values where the determinant is non-zero. That is ridiculous. What does this mean again? This means replacing. Dude, this section is psychotic. It's like, why don't we devise the most inefficient way to compute A inverse? So what does this mean? This means replace the ith column with the jth column of the identity matrix, and then you take these determinants and you get the ij entry of A inverse. Oh my gosh. I really hope this doesn't get tested, because it's like, what the hell? Yes. Yes, I want to compute the inverse by taking 9 determinants. Why is this in here, bro? What? Hey, you want to take the inverse of a matrix? Yeah, I'm reading your chats. What's up, Miv Chen? Miv, I don't know. Anyways, yeah, this is linear algebra. We're learning about determinants. But yeah, man, this is hilarious. You want to find the inverse of this matrix? Let's take 9 determinants. All right, so let's think about this. So this is going to be A inverse 1 over the, but you actually, hold on. All right, so here we get the, okay, but now we gotta compute the determinant of A. So it's 1 over the det of A times the classical adjoint. Okay. We could compute determinant of A directly, but the following computation provides a check. Oh my god. Cramer's rule is also a theoretical tool. It can be used to study how sensitive the solution is to changes in an entry in B. All right, let me just write down the theorems. But this is wild. Okay, that's theorem 7. Theorem 8. A invertible n by n, then A inverse is equal to 1 over the determinant of A times the ad. Okay, whatever. I might not even do many problems from this. I might just go straight to the exercise because this is, I mean, like, this is lame. All right, here we go. This is cool. All right, I like the geometric understanding of determinants. That's why I like this picture so much. For me, that's the only way I'm going to remember what a determinant is. It's, it's take your unit length basis vectors or whatever, and it gives you how much is stretched out under the action of the transformation. Okay. In the next application, we verify the geometric interpretation of determinants described in the chapter introduction. Although a general discussion of length and distance in Rn will not be given into chapter 6, we assume here the usual Euclidean concepts of length, area, and volume are already understood for R2 and R3. If A is a 2 by 2 matrix, the area of the parallelogram determined by the columns of A is the absolute value of det A. If A is a 3 by 3, it's the volume of the parallel pipe head determined by the columns of A. Is the absolute value. Okay. All right, so for a diagonal matrix, yeah, this is obvious. Because just imagine that instead of, let's see before. Well, just imagine you have like an A here and a D here on the diagonal. Then the product of A and D is going to be equal to the area of that rectangle. Oh, this is what I should have done. I should have pointed to this. So yeah. It will suffice to show that any 2 by 2 can be transformed into a diagonal matrix in a way that changes neither the area of the associated parallelogram nor the absolute value of the determinant. From 3.2, we know that the absolute value of the determinant is unchanged when 2 columns are interchanged or a multiple of one column is added to the other. And it is easy to see that such operations suffice to transform A into a diagonal matrix. Yeah, that's true. Column interchanges do not change the parallelogram at all. Column interchanges, yeah. So it suffices to prove the following simple geometric observation that applies to R2 and R3. Let A1 and A2 be non-zero vectors. Then for any scalar C, the area of the parallelogram determined by A1 and A2 equals the area of the parallelogram. Wait, what? What does that even mean? Oh, they're just saying that shears don't really. Oh, okay, I get it. Yeah, because this operation is like, what did they call it? They call it elementary row replacement. So elementary row replacement, they're just saying that it preserves. You can shear it and a parallelogram has the same area. To prove this, we may assume that A2 is not a multiple of A1. Otherwise, it would have zero area. If L is the line through 0 and A1, then A1 plus L is the line through A2. Wait, what? And A2 plus CA1 is on this line. The points A2 and A2 plus CA1 have the same perpendicular distance to L. Yeah, hence the two parallelograms have the same area since they share the same base. Okay, fine. A simple geometric argument. All right. Linear transformations. Translating a parallelogram does not change its area. Determinants can be used to describe an important geometric property of linear transformations in the plane and in R3. If T is a linear transformation and S is a set in the domain of T, then T of S denote the set of images of points in S. We are interested in how the area or volume of T on S compares with the area or volume of the original set S. For convenience, when S is a region bounded by a parallelogram, we refer to S as a parallelogram. What? Okay. S is a parallelogram, then the area of T of S is going to be the determinant of A times the area of S. Yeah. Okay, fine. We get the basic geometric things. I'm sure that they're restricting it to just the plane and a basic volume, but I'm pretty sure that that holds for any dimension. All right, we'll read through the proof. T of S is the parallelogram determined by the. Okay. And theorem 10 is just. We'll write down theorem 10. What was theorem 9? Okay. Finite region is S. Then, and T is linear transformation. Then T of S, det T of S is equal to det T times area of S. Okay. So it can look, the region can look like whatever, but use Cramer's rule. I'm probably not going to do that, honestly. All right, we'll read through them really quickly, though. Use Cramer's rule to compute the solutions. Okay, let's just remember, Cramer's rule is the rule that you can find solutions to AX equal to B, which is a system of linear equations, by taking a bunch of determinants. It's like really lame. All right, determine the values of the parameter S for which the system has a unique solution, and describe the solution. Compute the adjugate. Okay, so the adjugate. What is the adjugate again? The adjugate is you just take the cofactors of every element. Wait. Wait, so this is so you have to transpose this. So you take the cofactor for every element of this thing, then you have a matrix of determinants, then you take its transpose, and that's the adjugate. Okay. All right, let's just do the true falses. All right, we got 4 true falses. 2 parallelograms with the same base and height have the same area. Yep, that's true. Applying a linear transfer into a region does not change its area. That's false. If A is an invertible n by n matrix, then A inverse is equal to ADJ. Nope, that's wrong. You have to divide it by the determinant of A. Cramer's rule can only be used for invertible matrices. Now that, I believe, is true. Yes, that is true. Okay, so what were our answers? It was true. 36 is false. 37 is false. And 38 is true. Let's just double check. All right, so let's see. Test the inverse formula. Okay, good. There's 40 exercises in this thing. Actually, there's some fun geometric ones in here. It's all about computing volumes and stuff like that. But oh my gosh, come on. We're about to get to the good stuff, man. We're about to get to the real meat of linear algebra. Chapter 4. Let's go, dude. I'm so excited for this chapter. I've been waiting for this. Because that's the meat of linear algebra for sure. True, false, false, true. Okay, good. We're good. All right, so this is probably like 30 minutes. Yeah, it was 30 minutes. I just rushed through this one. I really didn't. Yeah, all right. I don't have a problem with this one being short. All right, peace.